So, when the duct is very long, there is enough area to heat transfer take place from and to the flow stream, and consequently the flow is not adiabatic. However, the flow often reaches an approximate isothermal state, and this flow can be analyzed as isothermal flow in a duct. And the most common example of such type of flow is transporting of gas over a long distance through pipes. Now, question usually comes that a transportation of gas over a long distance through pipe is essentially takes place at quite a low speed. Then should the flow be treated as compressible, or it can be treated as incompressible. However, the flow Mach number is usually quite low for gas transportation through a pipe. However, over a long distance a substantial change in pressure takes place, and which necessitates the for more appropriate analysis the flow should be treated as compressible. Now, essentially the analysis is similar to the adiabatic flow analysis that we have already discussed, with some minor verification. First of all, since the flow is not adiabatic, the total temperature T 0 is not constant, it is changing from point to point. Remember that T 0 is the total temperature that the flow would have reached if it were brought to rest adiabatically. So, at any point corresponding to a particular T, there is a T 0, and in this case this T 0 changes through along the flow. And so, if we use these in a duct with friction, the duct is of course of uniform cross sectional area. So, that A really does not appear in the equations. So, T is constant in this case, but T 0 is not. Now, in this case the energy equation takes the form dq equal to Cp dt plus d square by 2, that equal to Cp dt 0. Since by definition T 0 is T into 1 plus gamma minus 1 to m square, this implies dt 0 by T 0 equal to gamma minus 1 m square by 2 into 1 plus gamma minus 1 by 2 m square into d m square by m square will denote this as equation number 2 and this as equation number 1. So, the equation of state for a perfect gas equation of state that is P equal to rho at T for a perfect gas, and this implies dP by P equal to d rho by rho. T is constant and we denote this by equation 3. And since T is constant, speed of sound A is constant. And m square equal to u square by a square, this gives dm square by m square equal to 2 du by u. And the continuity, momentum and energy equation, continuity and momentum equations remain same, and consequently from continuity what we have obtained in the case of adiabatic flow equation, we get the same relation d rho by rho plus half of d u square by u square equal to 0, and this we call equation number 5. Similarly, from momentum conservation, we get the same equation that we had in case of adiabatic flow with friction in a uniform area duct, namely dP by P by gamma m square by 2 into 4 f dx by d plus gamma m square by 2 d u square by u square equal to 0. And from the definition of stagnation pressure, this will be our equation 6. This gives us as before d P 0 by P 0 to dP by P plus gamma m square by 2 divided by 1 plus gamma minus 1 by 2 m square into d m square by m square. We can write again another equation for impulse function. However, the impulse function for this problem is not very important in this case, and consequently, we are not going to use the impulse function. So, hence we have here once again 6 equations, that is from equation 2, 3, 4, 5, 6 and 7 with seven unknown, 6 equations with 7 unknown, and once again we choose that six equations equation 2 to equation 7 with 7 unknowns, and we once again choose 4 f dx by d as the independent one. Now, solving these 6 algebraic equations, that is equation 2 to equation 6, what we get is dp by p is d rho by rho equal to minus d u by u, that is minus half d m square by m square. This is equal to minus gamma m square by 2 into 1 minus gamma m square into 4 f dx by d. We also have d p 0 by p 0 equal to gamma m square into 1 minus gamma plus 1 by 2 m square by 2 into gamma m square minus 1 into 1 plus gamma minus 1 by 2 m square into 4 f dx by d, and dt 0 by t 0 equal to gamma into gamma minus 1 m to the power 4 by 2 into 1 minus gamma m square into 1 plus gamma minus 1 by 2 m square 4 f dx by d. Now, we see that in this case the sign of these terms depends not m square alone, but on gamma m square, or the direction of change depends on gamma m square, but not m square alone. So, this shows sign of the terms that is direction of change depends on gamma m square, but not on m square alone. Now, 4 f dx by d is positive always. Hence, we can see that the pressure will decrease if m square is less than 1 minus gamma, sorry, if m square is less than 1 by gamma. However, it will increase if m square is greater than 1 by gamma. Similarly, the other parameters will also, the sign of these other parameters, that is density change, velocity change, change in Mach number, change in total pressure and total temperature, will depend on whether m square is greater than or less than 1 by gamma. So, we can summarize this change in this, that if m is less than 1 by root gamma, this is of course, the flow is subsonic, and the other case is m greater than 1 by root gamma. In this case, it might be subsonic or supersonic both. What we see, that if m is less than 1 by root gamma or m square is less than 1 by gamma, pressure in this case decreases, while in this case pressure increases. The density too decreases and increases in this case. U increases, in this case it is decreases. M increases up to 1 by root gamma, and in this case decreases up to root 1 by gamma. T0 increases, in this case it is decreases. P0 decreases. However, coming to P0, we see another situation, that when m square is greater than 1 by gamma, that is when this is positive, there is a possibility that this term can still be negative, giving this sign to be negative, that is P0 may decrease. And however, there is also the possibility that this term may be positive when m square is greater than 1 by gamma. Numerator is of course positive, the denominator can also be positive for certain value of m, giving dP0 by P0 as positive, meaning that the stagnation pressure may increase for some specific value of Mach number, which we can see that it is increases for m less than square root of 2 by gamma plus 1, but decreases otherwise. That is, for Mach number greater than 1 by root gamma, but less than square root of 2 by gamma plus 1, the stagnation pressure increases. However, when Mach number is greater than square root of 2 by gamma plus 1, stagnation pressure decreases. What we find here, that the Mach number always tends towards infinity, 1 by root gamma. Mach number tends to 1 by root gamma. However, 1 by root gamma is essentially subsonic. So, implies in this isothermal flow, the subsonic flow will always remain subsonic. However, the supersonic flow may come down to a subsonic flow with minimum Mach number of 1 by root gamma. Also, we see that when Mach number is less than 1 by, if Mach number is less than 1 by root gamma, heat is added to the flow stream if m is greater than 1 by root gamma. Heat is rejected by the stream since the subsonic flow accelerates to the maximum value of 1 by root gamma, maximum value of Mach number 1 by root gamma, and subsonic flow decelerates to the minimum value of 1 by root gamma. So, you can see that that can be the maximum length of the duct possible, where flow Mach number reaches 1 by root gamma. So, maximum duct length possible corresponds to m and again this maximum duct length, if we denote it by L max, then once again we can integrate the relation from 0 to L max, and at 0 we consider Again defining an average friction factor, this gives us 4 F bar L max by D to 1 minus gamma m square by gamma m square plus log of gamma m square. Now, let us denote the properties. Properties at m equal to 1 by root gamma are denoted u star u star t, p star t, that is T to represent an isothermal, that is this is u star isothermal case and p star isothermal case, and rho star t and so on. Then hence the parameter m square by u square can be written as 1 by gamma, and this is u star t square. Since we have m square equal to u square by gamma r t and t is constant, this gives us u by u star t equal to root gamma into m. And rho by rho star t using continuity in a uniform duct is 1 by root gamma m. Now, using perfect gas relationship, for constant T, we have P by P star T is same as rho by rho star T, which is also 1 by root gamma m. Now, using the definition of stagnation pressure, we also have P 0 by P 0 star T equal to P by P star T 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1 divided by 1 plus gamma minus 1 by 2 into 1 by gamma to the power gamma by gamma minus 1. And substituting the value for P by P star T, this becomes 1 by root gamma into 2 gamma by 3 gamma minus 1 to the power gamma by gamma minus 1 into 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1 by m. The stagnation temperature accordingly can also be written as T 0 by T equal to T 0 by T 0 star T is T by T star T into 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 into 1 by gamma, which is 2 gamma by 3 gamma minus 1 into 1 plus gamma minus 1 by 2 m square. The length over which flow passes from M 1 to M 2 is given by 4 f L by D, or L is this required length, is 4 f M 1 and M 2, and using the relation that have been obtained for 4 f L max by D, we get 1 minus gamma M 1 square by gamma M 1 square minus 1 minus gamma M 2 square by gamma M 2 square plus log of M 1 square by M 2 square. We have already seen that P 1 by P 2 is same as M 2 by M 1 or M 2 equal to M 1 into P 1 by P 2, and substituting this relationship here, we get 4 f per L by D into 1 minus P2 by P1 square by gamma M1 square minus 2 log P1 by P2. Now, since M2 cannot exceed 1 by root gamma, M2 cannot exceed 1 by root gamma, and this gives P2 by P1 square is less than gamma M1 square. Now, if you have a fixed value of M1 and also of fixed friction coefficient, then we have two solutions for P2 by P1. This relation clearly shows that if we have a fixed value of M1 and a fixed value of the friction for FL by D, then we have two possible solutions for P2 by P1. However, only one of them is acceptable, the other is not, because that violates the second law of thermodynamics. So, for fixed M1 and 4 by D, two possible solutions exist for P2 by P1. However, one is acceptable, the other violates second law of thermodynamics. If we consider a very small power drop, small pressure drop, a small in percentage, and then we can expand this relation in power series of this fractional pressure drop. Assuming small fractional pressure drop, that is P2 minus P1 by P1 the relation power series of P 2 minus P 1 by P 1 and this gives 4 F bar by L D is 2 by gamma m 1 square into P 1 minus P 2 by into 1 minus gamma m 1 square minus 1 plus gamma m 1 square by 2 into P 1 minus P 2 by P 1, where higher order terms are neglected. And we can see that this formula is similar to the conventional pressure drop formula in incompressible flow, where of course, this term within the square bracket is just unity. Now, solving this quadratic equation, to 1 minus we see that in this solution the plus term is dropped, because that is not physically acceptable solution, as it violates the second law of thermodynamics. So, this gives the pressure drop over a portion of or over a length of the duct given by L, where the average friction factor is F bar, and this also is a measure of the power required to drive this flow through a duct of uniform area over a length L. We have also seen that for a given value of m 1, there is a maximum length for continuous isothermal flow, and at the end of that length, there is the Mach number reaches is 1 by root gamma. Hence, it follows that a choking effect may occur in similar fashion to those for adiabatic flow. However, one thing should be noticed here very clearly, that as Mach number is very close to 1 by root gamma, the changes in all the parameters are very rapid. That is, looking back to the relations for dP by P or any of these, that all these relations suggest that the change in the parameters is very fast when the Mach number is very close to 1 by root gamma, and consequently, in that rapid change the assumptions of approximately isothermal flow even may not hold. That is, when the flow reaches very close to m equal to 1 by root gamma, it is most likely that the flow will be there nearly adiabatic instead of nearly isothermal. However, looking from our simplified analysis of one dimensional isothermal flow, what we have seen that for a long duct, over a long duct with uniform cross sectional area where friction is present, the flow reaches or tends to a Mach number 1 by root gamma, and we have, as you have seen here, that if the flow is subsonic, that is the maximum Mach number then can reach 1 by root gamma, that is the flow still remains subsonic in this case. However, in the supersonic case, the flow Mach number can come down to 1 by root gamma, which is subsonic. That means, a supersonic flow when flows isothermally in a long duct with uniform area and friction can become subsonic. We have seen that the parameters pressure, density decreases in the duct for Mach number less than 1 by root gamma. However, they increases if the Mach number is less than 1 by root gamma. Similarly, the parameter flow velocity, flow Mach number, total temperature increases for flows with Mach number less than 1 by root gamma. However, they decreases if the flow Mach number remains larger than 1 by root gamma. The stagnation pressure decreases for Mach number 1 by root gamma. However, for the Mach number root more than 1 by root gamma case, there is a region or there is a range of Mach number which lies between 1 by root gamma and square root of 2 by gamma plus 1. In that range, the stagnation pressure increases. However, if the Mach number is outside this range, that is the Mach number is greater than square root of 2 by gamma plus 1, then stagnation pressure decreases. We have also seen that when Mach number is less than 1 by root gamma, because of the friction, heat is added to the flow and it is rejected by the flow when Mach number is 1 by root gamma. We have also seen what will be the length of a duct required to change the Mach number from M1 to M2, and we have also seen that what will be the pressure drop over a length L, over which Mach number changes from M1 to M2 and pressure decreases, pressure changes from P1 to P2. So, that concludes our discussion on isothermal flow in a long duct with friction. Next, we will consider a third problem belonging to this category of flow problems, that is flow in a duct, which is flow in a duct with heating or cooling. See, in a duct the flow can changes because of change in area, because of friction, or because of heating or cooling. We have already considered change in area, only change in area. Also have considered change only in the friction, presence of friction or no friction, but similarly now we will consider when there is simply heat is added. However, a combination of all these or any two of these three is practical and quite possible, and they are perhaps more realistic. However, they can not be solved analytically even in one dimensional framework. So, anyway, our next problem of discussion will be flow in ducts with heating or cooling. With that, we